Historical temperature data provide an important test of our understanding of past climate change. However, these data were primarily collected for the recording of daily variations in weather, rather than the gradual changes associated with global warming. In order to accurately measure the climate signal in the data, the historical records must be calibrated to remove the effects of instrumental changes. This process is called homogenization. Given that this topic has received some attention in the media, I have produced a report evaluating the need for and effectiveness of climate data homogenization. The report covers a number of questions, such as whether there are inhomogeneities in the data and what they look like. This video will cover just one part of the report, in particular the question of whether there is evidence for a bias in the most widely used homogenization method. The question arises because the homogenized weather station data show a slightly greater global warming signal than the raw data, with most of the difference occurring around the middle of the 20th century. Recent temperature trends are largely unaffected. Some people have suggested that the increased warming seen in the homogenized data is evidence of a bias in the homogenization methods. The most widely used homogenized weather station data come from the Global Historical Climatology Network, or GHCN, a project of the National Oceanographic and Atmospheric Administration. Their pairwise homogenization algorithm is described in this paper. Why does homogenization increase the trend in the global mean temperature? There are two possibilities. The first is that the data themselves contain evidence of inhomogeneities which require a downward correction to earlier temperature observations. The second is that the corrections are an artifact of the analysis method. In other words, they're a bias in the calculation. There are two ways to find out which is the case. Firstly, we can look at the data to see if we can find independent evidence for a trend in the inhomogeneities. Or secondly, we can apply tests to the GHCN software to try and find evidence for a bias. One way to evaluate an adjustment is to compare the weather station to the mean of the nearby stations. Here is a simple case, with the station in blue and the local mean in green. A 6-year window centered on the date of the adjustment is shown. The station shows good agreement with its neighbors, apart from the big jump in November 1976. Most cases are less clear-cut than this, of course. We can look at all of the GHCN adjustments and classify them by size and direction, shown in the following histogram. Very small inhomogeneities are undetectable, so there's a gap around 0. Adjustments can be either positive or negative, but there are very slightly more upward adjustments than downward adjustments, which causes the homogenized data to show slightly more warming. The neighbor comparisons can then be used to work out how big the adjustments should be by working out the shift required to align the two halves of the station record to its neighbors. We can do this for all the GHCN adjustments and compare the shifts from the 6-year window to the shifts from the GHCN method. Each cross on this plot represents one of 5,000 adjustments analyzed in this way. The x-axis is the GHCN adjustment, and the y-axis is the window estimate. The methods show good agreement. Furthermore, the window method also shows more upward than downward adjustments, giving a very similar trend to the GHCN method. However, this analysis is similar to that performed by the GHCN software, so all we have shown so far is that the trend in the adjustments doesn't seem to arise from a bug in the GHCN code. Ideally, we'd like to evaluate the adjustments against an independent source of temperature data. Weather model reanalyses can be used to reconstruct historical temperatures without using the weather station thermometers. The modern era retrospective analysis uses data from weather satellites to produce an independent temperature record for the satellite era. Reanalyses have limitations when looking for climate signals due to the constant replacement of satellites. However, they may provide useful information for the short window surrounding an adjustment. We can use the same window method as before, but this time using the nearest temperature from the reanalysis data instead of the mean of the neighbouring stations. The results of this analysis are shown for 1300 adjustments in the satellite era. Again, the results support the GHCN adjustments. To check the pre-satellite adjustments, we need a reanalysis which goes further back in time. The 20th century reanalysis is based on temperature data from ships and air pressure data from weather stations, and so also provides an independent check on the weather station thermometers. With this reanalysis, we can check over 6,000 adjustments. There's a little more spread due to the uncertainties in the reanalysis, but the results again show slightly more upward than downward adjustments, further supporting the GHCN result. The second method for testing for bias involves running the GHCN software on specially prepared datasets to provide a direct test for biases in the software. This requires the software to be downloaded, compiled, and run. I've provided the commands needed to do this in the methods data on the website. The first test is to rerun the GHCN software on the raw data and confirm that the homogenized data do indeed show greater warming. The global mean of the raw and homogenized data are shown here. The red line shows the raw data, and the blue line the homogenized data. The lower panel shows the difference between the two. Homogenization produces an increase in the warming trend, with most of that increase occurring between 1925 and 1975. But could that increase arise from a bias in the software? One possibility is that the software might preferentially find positive rather than negative adjustments. How could we test for this? A very simple test is to invert every raw station record, in other words, swap hot for cold. If the GHCN method favours upward adjustments, homogenizing the inverted stations should have a warming effect, or rather reduce the cooling in the inverted record. So what does happen? Here are the results. In the original data, homogenization increased the warming trend. In the inverted data, homogenization increases the cooling trend. The GHCN algorithm does not appear to favour adjustments in one direction over the other. But maybe the bias is more subtle. Perhaps the algorithm tends to amplify any trend in the data, whatever the direction. We can test for this by inverting the trend for each station while preserving the month-on-month variation. If the GHCN method amplifies trends, then it will amplify the cooling trend in the modified data. Here are the results. In this case, the homogenized data show less cooling than the raw data. In fact, the effect of the adjustments in the lower panel is almost identical for the original and the trend-inverted data. The GHCN algorithm shows no tendency to amplify the trend in the data. To summarize, we have looked at tests which would tell us if the GHCN method were biased in favor of upward adjustments, and if the method were biased in favor of increased trends. In both tests, the method shows no signs of bias. There are a number of other tests in the full report. Supporting data are available on the project website. This includes all the computer code required to reproduce the results from the report. The computer code is available from the Methods and Data page.